Hello students, welcome to the fifth video for the thermodynamics. In this video, we will cover thermodynamic heat and thermodynamic work. Thermodynamic heat and thermodynamic work both cannot stored in a body. These are not storable form of energies. Even if you take the cup of hot coffee, the heat energy present in the hot coffee is 0. Similarly, even if you take the chicken piece, hot chicken piece, the heat energy present in the hot chicken piece is 0. But when you keep the hot chicken piece in your mouth, the tongue in your mouth may be maintaining 40 degrees centigrade. The hot chicken piece may be maintaining around 120 degrees centigrade. Because of the temperature difference between the hot chicken piece and your tongue, some energy is entering to your tongue from the hot chicken piece. That energy which is entering to your tongue from the hot chicken piece is the thermodynamic heat. So thermodynamic heat is also a kind of energy which is crossing the boundary of the system only because of the temperature gradient or temperature difference. It is like this. Let us take a system. This is your system. As we know, this is the boundary and surroundings. Assume the temperature maintained by the system 20 degrees centigrade. Surroundings maintained, the temperature maintained by the surroundings may be around 50 degrees centigrade. Because of the temperature difference between the system and surroundings, some energy is crossing the boundary of the system from high temperature to low temperature region. That energy which is crossing the boundary of the system due to temperature gradient is called thermodynamic heat. So from this, the definition for heat is a kind of energy which is crossing the boundary of the system only because of the temperature gradient is called thermodynamic heat. The sign convention for thermodynamic heat is like this. If I assume the system temperature is 20 degrees centigrade, surrounding temperature is 100 degrees centigrade, since the surroundings are maintaining high temperature than the system temperature, here heat energy is transferring from surroundings to system like this. Since the heat is entering to the system, that kind of heat entering to the system can be called as heat supplied to system. That kind of heat thermodynamically can be taken as positive heat. Here positive heat means the system is receiving the heat energy. Similarly, if I take another system, one more system, in this case system may be maintaining around 80 degrees centigrade, surroundings may be maintaining around 15 degrees centigrade. For this case, since the system is maintaining high temperature than the surrounding temperature, here the energy is transferring from system to surroundings. Here energy is transferring from surrounding to system. That kind of heat energy can be called as heat rejecting from the system. Heat rejecting from the system is thermodynamically taken as negative heat. Negative heat means the system is losing the heat energy. Positive heat means the system is receiving the heat energy. The system receiving heat energy thermodynamically called as positive heat. The system losing heat energy to surroundings is thermodynamically taken as negative heat. The general relation between thermodynamic heat and temperature gradient is the heat transfer generally denoted by Q. Heat transfer is proportional to mass of the system multiplied by temperature gradient. This is the general relation between thermodynamic heat and temperature gradient. For eliminating the proportional limit, we are putting a constant like this. Heat transfer Q equal to some constant C into M into dt, where C equal to Q by M into dt. That C is called specific heat. That specific heat is defined like this. The amount of heat supplied to 1 kg mass of gas, the amount of heat supplied to 1 kg mass of gas to rise the temperature through 1 degree centigrade or 1 Kelvin is called specific heat. Once again, the amount of heat supplied to 1 kg mass of gas or 1 unit mass of the gas to rise the temperature through 1 degree centigrade or 1 Kelvin is called specific heat. Its units is, heat is a kind of energy may be measured in kilojoules. Kilojoules per mass is kg. Here temperature difference can be written either in Kelvin or degree centigrade. It can also be written as kilojoules per kg degree centigrade. Kilojoules per kg Kelvin or kilojoules per kg degree centigrade is the unit of specific heat. Remember, all materials which are available in the market are maintaining two specific heats, namely specific heat at constant pressure and specific heat at constant volume. But the difference between the Cp and Cv for both liquids and solids is very, very small. That's why generally we are ignoring the difference between the Cp and Cv for both liquids and solids. But for the gases, whereas for the gases, there is a observable gap between the specific heat at constant pressure and specific heat at constant volume. That's why we are considering two specific heats for the gases. Specific heat at constant pressure means the amount of heat supplied to 1 unit mass of working material to rise the temperature through 1 degree centigrade at constant pressure is called specific heat at constant pressure. That specific heat at constant pressure denoted by Cp. Similarly, Cv is the specific heat at constant volume. Definition is the amount of heat supplied to 1 unit mass of working material to rise the temperature through 1 degree centigrade or 1 Kelvin at constant volume is called specific heat at constant volume. Remember, the specific heat at constant pressure for any gas always greater than specific heat at constant volume. Now let us discuss what is the physical meaning of Cv and Cp. The Cv physical meaning is like this. Let us take a cylinder with piston mechanism or a closed system. As we know, in the closed system, only energy is crossing the boundary of the system in the absence of mass. This is my piston. Inside the cylinder, I took some gas. Assume that gas is maintaining the mass 1 kg. The initial temperature of the gas is 20 degrees centigrade. If you want to supply the heat at constant pressure, the piston must be arrested. the piston must be arrested for supplying the heat at constant volume. It is like this. I am arresting the piston. Once we arrest the piston, though some energy is given to the gas, the piston cannot be moving because the piston is fixed by something. Now I am supplying some heat to the gas. Assume I am supplying some 500 joules of energy. 500 joules of energy for 1 kg mass of gas. While I am supplying 500 joules of energy for 1 kg mass of gas, let us assume the temperature of that 1 kg mass of gas is increasing from 20 degrees centigrade to 21 degrees centigrade. Then I can say this is the specific heat happening, or this is the amount of heat which is given for 1 kg mass of gas to rise the temperature from 20 degrees centigrade to 21 degrees centigrade at constant volume. In this case, volume is remaining constant because the piston is not moving away. So anyhow, this 500 joules of energy is causing for increasing the temperature of 1 kg mass of gas from 20 degrees centigrade to 21 degrees centigrade at constant volume. Then this is equal to specific heat at constant volume. Specific heat at constant volume means the amount of heat supplied to 1 kg mass of gas to rise the temperature through 1 degree centigrade at constant volume. So specific heat at constant volume is 500 joules. Now let us talk about the specific heat at constant pressure. For discussing the specific heat at constant pressure, the heat must be supplied at constant pressure. Again, let us take the cylinder with piston mechanism. This space is covered by some gas. This space is covered by some gas. Let that gas is maintaining 1 kg. Initial temperature of that gas is 20 degrees centigrade. As I told you, to supply the heat at constant pressure, the piston should not be arrested. Because if the piston is arrested, it is becoming constant volume process. So now I am supplying some heat. Assumes the same amount of heat is supplied. 500 joules of energy is supplied to the system. While I am supplying the 500 joules of energy for 1 kg mass of gas, its temperature is naturally increasing. Along with temperature, pressure of the gas also increases. With that pressure, in this case, the local atmospheric pressure is acting vertically downwards on the piston. The gas pressure inside the cylinder is acting vertically upwards on the piston. By the time I am supplying the heat to 1 kg mass of gas, temperature of the gas increases. Along with the temperature, pressure of the gas also increases. With that pressure of the gas increases means the gas pressure may be more than the local atmospheric pressure. Because of the more pressure inside the cylinder, that high pressure gas is lifting the piston like this. Once the piston is lifting up, we are getting some thermodynamic work. Once again, we are assuming that initially the piston is at equilibrium condition. The condition for equilibrium is vertically upward force must be equal to vertically downward force by ignoring the self weight of the piston. Initially, the vertical upward force on the piston equal to vertically downward force. Now by the time I am supplying the heat to the gas, temperature of the gas increases. Along with temperature, pressure of the gas increases. Then the gas pressure inside the cylinder will be more than the vertically downward pressure force. That's why with that high pressure, the gas is lifting the piston. The gas is lifting the piston means some work we can get from the system. Assume the energy which is causing for lifting the piston may be 200 joules. The energy which is causing for lifting the piston is 200 joules. That means among the 500 joules of energy, 200 joules of energy is wasted for lifting the piston. Then the remaining energy which is causing for increasing the temperature is 300 joules only. As we know, for increasing the temperature from 20 degrees centigrade to 21 degrees centigrade, 500 joules of energy is required. Though I give 500 joules of energy, this full energy is not utilized for increasing the temperature because a part of the energy is used for lifting the piston. Therefore, whatever the energy which is causing for lifting the piston to be additionally supplied, that is 200 joules. Now when I give 700 joules of energy, in this case, this 200 joules of energy is causing for lifting the piston. Remaining 500 joules of energy is causing for increasing the temperature from 20 degrees centigrade to 21 degrees centigrade. You may have doubt that, sir, how we can maintain the constant pressure in this particular case? Very easy. By the time we are supplying the heat, because of the heating the gas, definitely pressure of the gas increases. With that pressure, the gas is lifting the piston. By the time the piston is lifting up, along with the piston, gas is expanding. Because of the expansion of the gas, the pressure of the gas decreases. The combined effect of increase in pressure by supplying the heat and drop of pressure due to expansion, this combined effect may be maintaining the constant pressure. That is how you can practically maintain the constant pressure during the heat supplied to a gas in a closed system. Without allowing the expansion, it is impossible to supply the heat at constant pressure as a closed system. Anyhow, this 700 joules of energy must be supplied to increase the temperature from 20 degrees centigrade to 21 degrees centigrade of 1 kg mass of gas at constant pressure. The 700 joules is coming under specified constant pressure. Here Cp is 700 joules, Cv is 500 joules. Here Cp, right? Cp is greater than Cv for any gas except at absolute zero state. In the last video we discussed, at absolute zero state, the Cp and Cv both are identical. Other than at absolute zero state, the Cp always greater than Cv.